Welcome to Algebra 2. This is section 5.2, Properties of Exponents and Radicals. So we talked a little bit in our last section about dealing with nth roots and how that applied to exponents. So we've got that same list of properties of exponents. Now we're just going to explore how the exponents apply to radicals a little bit further. Right, so we're adding in some properties of radicals, and the product property of radicals says that if I have the nth root, it could be any root of the product of two numbers, then that is equal to the nth root of the first number times that same root of the second number. And if we have any question as to why that is the case, it ties in really closely with our exponents. So think about what a to the nth power really means. Well, that's a, or to the nth root, I should say. It's a to the 1 over n power. And if I multiply that by b to the 1 over n power, that makes sense. We've got a power that is being applied to two different bases. That's the same thing as a times b to the 1 over n power. So we're taking that exponential property, that property of exponents, and just applying it to work with radicals here. And the same is true for the quotient property. If I have the nth root of a quotient of a fraction, that is the same thing as the nth root of the numerator over the nth root of the denominator, and it comes from the same exponential properties. All right, so one of our tasks is going to be simplifying radicals. And an expression involving a radical with an index is in simplest form when we have these three conditions met. So we have no perfect nth powers underneath our radical sign. That's what it means to be a part of the radicand. We have no fractions underneath our root symbol, our radical symbol, no radicand that contains fractions. And no radicals end up appearing in the denominator of a fraction. Okay, so this concept, this is where we formally learn how to rationalize the denominator. We turn the denominator into a rational number by multiplying the expression by an appropriate form of 1 that eliminates the radical form. In other words, we want to create a power that is perfectly underneath the root. So we would want to create like a cubed term underneath a cubed root so that we get the powers and the roots to cancel out. So that's going to be our goal, to make those denominators rational numbers. It gets a little bit more complex if we have a denominator that is not just a radical term, but it's a sum or a difference of two terms. We multiply by the conjugate. And all that is it's the same expression, but we change the sign in between. We are trying to set up factors that looks like factors that were a difference of squares. And you'll see why as we go through an example. If we have a difference of squares multiplied together, what we end up with are really two terms that end up being squared, or in our case for other roots, what ends up happening is the root ends up getting canceled when we FOIL them together. If we are adding or subtracting radical expressions, then we must make sure that they are right, or like radicals. And to add or subtract them, we really are just using the distributive property and combining like terms, but our terms are really radicals, numbers that contain radicals. All right, so let's put some of this into work. A lot of times the examples speak a lot louder than the actual textbook jargon. So number 6 here, this is not considered to be proper form because this 7 to the 1/3 power that is a denominator, what we've really got is 7 over the cubed root of 7. So it is not considered simplified. We have some work to do. Now what I would do, personally, we could always change it into radical form like this and simplify it that way. But the exponents, we have a very fortunate situation where our numerator, we could consider that 7 to the 1st. It has the same base as the denominator, 7 to the 1/3. So if I have 7 to the 1st over 7 to the 1/3, I could express that as that same base with the difference of those two exponents. So it's really 7 to the 2/3 power. And I think we could simplify that a little bit further. I mean, they started with a rational exponent, so technically this is a rational exponent in our answer. But what that really means, if we tie this into section 5.1, The denominator is a 3. That's making the number smaller. It's a third root of 7 squared. Oh, that's the same thing as the cubed root of 49. So that's another way of expressing 7 to the 2/3 power. And I think that looks a little bit simpler than 7 to the 2/3. That's just a matter of personal preference there. Again, either of those box solutions, we have simplified the expression. Number 10. Here, we've got multiple properties of exponents, and we could apply them really in any order as long as we account for everything. So here, what I notice is inside parentheses, I'm kind of a stickler for following the order of operation. Let's do the work in parentheses first. So I've got a product of two numbers with like bases. So really, inside those parentheses, I've got 5 to the 1/2 plus -3/2. And then all that's being raised to the -1/4. Well, if I simplify that exponent, 1/2 plus 3/2 is a -1, and that's being raised to the -1/4. Now I can apply my power to a power property of exponents, which means I multiply those together. I could call that a base of 5 to the -1 times -1/4 power, 5 to the +1/4 power. And again, since we started with rational exponents, this is an acceptable simplified answer, but I would get any bit of practice that I can converting that into radical form. The 1/4 power is like the 4th root of 5 to the 1st, or just the 4th root of 5. So either of those are considered simplified. So there we use properties of exponents to simplify. We can also use properties of radicals to simplify. Sorry, I accidentally brushed the tablet there. Let's erase that away. Go back to our pen. So for number 14 here, what we've got, a product of two radical numbers, and they have the same root. So I can combine those together and call it the cubed root of 16 times 32. All right, so this may require a calculator to work out, but we can go through it that way. Another approach, if we wanted to avoid using a calculator, would be to simplify, find perfect cubes underneath this cubed root. So for 16, I'm actually going to split this up before I combine it back together. It's going to make the number work a lot easier. And please realize that this would lead us to the correct answer as well. So here I've got the cubed root of, let's see, 16. A perfect cube is 8 times 2 times, then I've got my cubed root of 32. Well, that's 8 times 4. Okay, well, I can break apart each of those. Say that first one is the cubed root of 8 times the cubed root of 2 times another cubed root of 8 times the cubed root of 4. I can group these two cubed root 8s out front. That's the cubed root of something that's clean. It's a perfect cube. It's really a 2 times another 2 times the cubed root of, what do I have left? The cubed root of 2 and the cubed root of 4. I could combine those together. So I've got 2 times the cubed root of 8. Hey, that's another perfect cube underneath a cubed root. I'm really doing 2 times 2 times 2. It's an 8. So going back to this first method, if we had a calculator that we were allowed to use, 16 times 32 is 512. And then we would, of course, see, is there any perfect cube underneath? And if you've been making lists of perfect cubes as we've been working with them, you know that 512 is 8 cubed. So I've got the cubed root of a number that is 8 cubed. The answer is just 8. So multiple ways. One way of working it out by hand, done over here on the right. If we have a calculator, then the method on the left would end up being easier. Let's take a look at number 20. So here I've got the cubed root of 3 times the cubed root of 18. Okay, I can multiply those together because they have the same index on the root. They're both cubed roots. That's the cubed root of 3 times 18. That's 54. And then in my denominator, I've got 6th roots. Well, the 6th root of 2 times another 6th root of 2. That is the 6th root of 4. I can multiply those 2's together under one of those radicals since they had the same index. All right, well, this is a little bit trickier to spot because, to simplify from here, I'd really like to get one radical, and I don't want any radicals left in the denominator. I'd like to make this one number if at all possible. And what I'd like to do is use the properties of exponents personally. But let's see what would happen if we just use properties of radicals. That's all the instructions are telling us, properties of radicals only. I do know that 27 is a perfect cube, so I'm going to call that cubed root of 54 the cubed root of 27 times 2. 27 times 2 is another way of writing 54. And I'm going to leave that denominator the sixth root of 4. All right, well, I can break apart that numerator. The cubed root of 27 is just a regular 3, and then I've still got the cubed root of 2 underneath. All right, and then in the denominator, this sixth root of 4, I could think of that as the sixth root of 2 squared. What would I need to multiply in to this sixth root of 4 to make a perfect sixth power underneath? I would need to multiply it by the sixth root of 2 to the 4th. That way I would take 2 squared times 2 to the 4th and get 2 to the 6th underneath that sixth root. So that's what I must do to avoid ending up with a radical in the denominator. I'm going to multiply the fraction that I have times the sixth root of 2 to the 4th over the sixth root of 2 to the 4th. And since I'm multiplying that by something that is really just a 1, right, it's something over itself, it's not changing the value at all, but it is going to clean up that denominator. So let's see what we've got so far. In the numerator, we've got 3 times the cubed root of 2 times the sixth root of 2 to the 4th, that's 16, and that's all over the sixth root of 2 to the 6th. Now we can cancel out because across the denominator we've established a sixth power underneath a sixth root. I've got 3 cubed root of 2 times the sixth root of 16 all over 2. Now it may seem like we can't simplify this any further, but we actually can. And it involves this sixth root of 16. Let's just step aside for a second and see what the sixth root of 16 actually is. The sixth root of 16 is actually 16 to the 1/6 power. And if we're a clever math student, I would like to create a fraction up here that simplifies to something over 3. That would be another cubed root. So I'm going to call this 16 4 squared. So I have the sixth root of 4 squared. I haven't changed the value of anything. I've just rewritten it. That could be called 4 to the 2/6 power, which is really 4 to the 1/3 power. I can simplify the fraction in that exponent. All right, so now let's rewrite what we had way back up here in this step. I've got 3 times the cubed root of 2 times that sixth root of 16. We said that's the same thing as 4 to the 1/3. That's the cubed root of 4 all over 2. That's 3 times, I can multiply those cubed roots together now, the cubed root of 8 all over 2. And the cubed root of 8 is a perfect cube. It's like 3 times 2 over 2. If you can believe that, that whole mess that we started with simplifies down to a 3. Now realize that this work is something that we could check in a calculator very quickly if we knew our properties. And we could have done these properties, applied them in a different order, and still wound up with the same result as long as we kept our goals of simplifying in mind. Example 3, write the expression in simplest form. Well, here to simplify a single radical term, what we're going to try and do is create a perfect fifth power underneath a fifth root. Try and get some type of cancellation to happen there. So the best way I can think to do this is actually with a factor tree. And that's just because in the case of a fifth root, we really don't have known lists of fifth powers. So let's start breaking apart this 288. 288 is 2 times 144, and 144, I could call that 2 times, 72. And I could break apart the 72, call it 2 times 36. Break apart the 36, that's 2 times 18. Break apart the 18, that's 2 times 9. And break apart the 9, that's 3 times 3. So really I'm taking the fifth root of 2 times 2 times 2 times 2 times 2, 2 to the fifth, times 3 times 3, well, that's 3 to the second. So what I've created in this situation through this factor tree, we've got this grouping of 5 2's multiplied together, and then that's being multiplied by these 2 3's, and that's creating that 288 underneath. I can simplify this part of the radical because I have a fifth power underneath a fifth root, so it's a regular 2. That root cancels out that power, and that's times the fifth root, it's still a fifth root, of 3 squared, 9. There is our simplified radical. We had hidden within that 288 a perfect fifth power underneath a fifth root. That's what it means by simplifying. For number 26, here we've got the cubed root of a fraction. Remember, that's the same thing as the cubed root of the numerator over the cubed root of the denominator. And what I need to do is figure out a way to multiply that fraction by something to eliminate the radical in the denominator. What I have already in the numerator is 3 root 7, and in the denominator I have the cubed root of 4, which is 2 squared. So I've really almost got a perfect cube underneath a cubed root. I simply need to multiply in the cubed root of 2 to the first into the numerator and denominator. Right? I just want to multiply by 1, and I will have my solution. So in the top, I've got the cubed root of 7 times 2, 14. We were able to multiply those together because they were the same root. And in the denominator, I've got the cubed root of 2 squared times another 2. That's 2 cubed. We got a perfect cube to cancel out our cubed root. Cubed root of 14 over a regular 2 after all those roots have been canceled out. That is our final answer. All right, and moving on here, example 3. Write it in simplest form again, but now we have conjugates. You can see how our denominator looks different. It's a sum or difference of radical terms, not simply a radical term. Whenever we spot that, we need to multiply by the conjugate. That would be 9 plus root 6 in the numerator and denominator. We're still just multiplying it by something that means 1, but it sets up the conjugates multiplied together in our denominator. In the numerator, when I multiply across the top to multiply these two fractions together, I need to distribute. So I have 99 plus 11 root 6. And in the denominator, I have two what look like binomials. I would need to FOIL those together. But here's the beauty of why we chose conjugates. Since it is like a difference of squares that have been factored out that we are going to multiply back together, the O and the I, the outside and inside in FOIL, don't matter. It's just first times first, last times last. And if I look at my two conjugates here, first times first is 81. Last times last is like negative root 6 times positive root 6. That is a negative root 6 squared, or just a negative 6. So in multiplying together, you can see that conjugate got rid of all radicals in the denominator. Our final answer is 99 plus 11 root 6 all over 81 minus 6, that is 75. For number 36, the same principle applies. We got a sum or difference of radical terms. We cannot combine those together and call it the square root of 8. Don't think that for a second. We did not have a difference property of radicals. I notice the difference, so I know I need to multiply the numerator and denominator by the conjugate of that denominator. Across the top, again, we need to distribute. That would be the square root of 70 plus the square root of 14. Remember, we can multiply things under the same radical. And then for our denominators, we've got our two binomial-looking numbers here. First times first plus the square root of 10 times itself. Square root of 10 squared is just a regular 10. Minus the square root of 2 times itself. I'm taking a negative root 2 times a positive root 2. That is just a regular 2. Root 2 times itself, squares it, gets rid of the square root. We have a 2. Final answer, square root 70 plus square root 14 all over 8. Okay, and naturally we would want to see, can we simplify any of these square roots? In this case we could not, but we may have to do a factor tree or simplify each of these radicals individually to see if we could make that entire result simplified further. Okay, example 4, simplify the expression. Remember, we can only add or subtract radicals if we have the same root and the same radicand underneath. All right, just like we can only add like a 3x with another x term, the same is true with our radicals as well. So the 27 root 6, I can't do anything with that. However, this 7 square root 150, it sure looks like I can simplify that. Is there a perfect square that goes into 150? Hey, 150 is 25 times 6, and 25 is a perfect square. So I've got 7 times the square root of 25 times 6. That is the same as 7 times a regular 5, because the square root of 25 comes out clean, times the square root of 6. So really, I've got 27 root 6's plus 35 root 6's, and I can combine those together to get 62 root 6's. So by simplifying the square roots, we were able to establish some like radicals and combine those together. Now let's look at 46. I've got 5 to the 1/4, which is the 4th root of 5, plus 6 times the 4th root of 405. And I want to break apart that 405, see if there is a perfect 4th root or a 4th power underneath that 4th root. So let's start breaking up the 405. I know it ends in 5, so it must be divisible by 5. That gives me an 81. 81 I know is 9 times 9. And if I break apart each 9, I get 3 times 3, 3 times 3. Oh, so this second term is really 6 times the 4th root of 3 times 3 times 3 times 3. That's 3 to the 4th times that one lonely 5 we had underneath. So hidden within this radical, we have a perfect 4th power underneath a 4th root. I've got 4 root 5. Sorry, not 4 root 5. The 4th root of 5 plus 6 times 3, 18 4th root of 5's. If I combine those together, I've got 1 4th root of 5 plus 18 4th root of 5's. That's 19 4th root of 5's for my final answer. Now, since they started off with rational exponents, we should probably convert our answer back to match how the question was given. So we would probably want to call this 19 times 5 to the 1/4 power. And that's just getting picky at the end. Either of these are equivalent. They both mean the same thing, and they both are a simplified expression. All right, and number 54. Here we've got a simplifying project where we've got an 8th root with a bunch of stuff going on underneath. Now our order of operations says that we want to handle grouping symbols first. And when I look at this, I sure see this nasty fraction as being a group of terms underneath that radical. So let's try and simplify that first. If I have n to the 18th and I divide away n squared, that means I have n to the 18 minus 2, n to the 16th. Likewise, if I have p to the 7th divided by p to the negative 1st, that's the same thing as p to the 7 minus negative 1, p to the 8th power. So really, what's happening underneath that 8th root is n to the 16th, p to the 8th. Ooh, and this p term is really nice because it's an 8th power underneath an 8th root. I know I can free or the eighth root will cancel out that eighth power. It's just a regular 1p out front. And then the eighth root of n to the 16th, there are a number of different ways of thinking of that. Eighth root of n to the 16th is the same as n to the 16 over 8. That's just a regular n squared. So I should have p to the first, n to the second for a final answer. Another way to justify that is that the eighth root of n to the 16th is like the eighth root of n squared to the eighth power. So again, we have an eighth root canceling out an eighth power, a couple different ways of reaching our final answer. All right, and example 5. Continuing on here, we've got 60 and 64. More of these like grouping, simplifying problems to work with our properties of exponents. And we should have covered a lot of these in Algebra 1, so hopefully we can get through a lot of this without too much trouble. Let's work with the grouping underneath in problem 60. Hidden within, I can see 405 over 5. And we did that in an earlier example. It's 81. I've also got x cubed over x to the negative first. That is x to the 3 minus negative 1, x to the fourth, our division of powers property. And lastly, I've also got y cubed over y. Well, if I divide away one of those y's, it's like y to the 3 minus 1 power. I'm just going to have y to the second. So my problem looks like the fourth root of 81 times x to the fourth times y to the second. All right, well, I do see one perfect fourth root, or fourth power, underneath my fourth root, so I can free that x. The root will cancel out the power there and just make an x. 81, we've already seen this a little bit earlier. 81 is 3 to the fourth power, so that's also like taking the fourth root of 3 to the fourth. Again, the root cancels out the power. All that's left underneath is this y squared, and I can simplify that. That's like y to the 2 over 4 power. Hey, that's the same as y to the 1/2 power. So my final answer should be 3x times the square root of y to the first. There's a lot of simplifying steps here, but really, once we have a knack for knowing all those properties, they really mesh together very, very nicely. All right, let's look at 64. Number 64, I see hidden out front, we've got a 7 divided by 56. I can simplify that to 1 over 8. Oh, I should clean that up. Okay, so our 7 over 56, sorry about that, was 1 over 8. I've also got x to the negative 3/4 over x to the negative 1/2. Well, that cleans up into x to the negative 3/4 minus negative 1/2. That's x to the negative 1/4. I've also got hidden in that fraction y to the 5/2 over y to the positive 1/4. So y is divided by y is y to the 5/2 minus 1/4. Well, that would be 10/4 minus 1/4. That's y to the 9/4 power. Okay, so here's part of my simplified result. Here's another part. Here is another part as well. And then I've also got a z to the negative 2/3. That has nothing else applied to it. Okay, so let's start putting all this together. I've got 1 over 8 times x to the negative 1/4 times y to the 9/4 times z to the negative 2/3. Oh boy, this has quite a bit. I know that anything that has a negative exponent is meaning the reciprocal, so I know this x to the negative 1/4 is really meaning 1 over x to the positive 1/4. Same thing happens with z. I've got z to the negative 2/3. That's 1 over z to the positive 2/3. we can start to see the multiplication take place. Across the top of all these fractions, I could think of that y to the positive 9/4 as that value over 1. Across the top, I've got y to the 9/4, which is like the fourth root of y to the 9th, over 8 times the fourth root of x to the first, times the cubed root of z squared. Holy cow, there's a lot happening here. Underneath here, this fourth root of y to the 9th, I could think of that as the fourth root of y to the 4th times another y to the 4th times y to the 1st, right? If I kind of break apart that exponent, 4 plus 4 plus 1 gets me the 9, but it sets up 2 perfect fourth powers underneath my fourth root. So really my numerator is y squared. I could free 2 of those y's times the fourth root of y. All over, I've got an 8, I've got a fourth root of x, and I've got a cubed root of z squared. So now I just need to deal with these radicals in the denominator. Well, in the numerator, I have to multiply in fourth root of x cubed, and I have to do that in the denominator as well. That will make a perfect x to the 4th under my fourth root. And then for my z's, I need to multiply in the cubed root of z into the top and to the bottom. That will make a perfect z cubed underneath that cubed root. Yikes. So final answer time. We've got y squared, and then we've got the fourth root of, we multiplied in x cubed. That was under a fourth root, and we also had 1y left under a fourth root, times the cubed root of z, all over. Let's see what we set up in our denominator. We had the 8 all along. Then we canceled out that fourth root with our x. It's just a regular x now. And we canceled out that cubed root with z. It's just a regular z now. That should be our final answer. If you can navigate that problem, you get it. There is no doubt in my mind that you get how these properties work together. Okay, and then I believe this is our final example, example 6. Perform the operation, assume all variables are positive. You can see that we've got some rational exponents and we've got some radicals in there as well. So we're combining the two strategies together. Let's clean up the parentheses. I've got the same base of p, and I'm multiplying those terms together. That means I can add the exponents. Call that p to the 1/2 plus 1/4 power, p to the 3/4, minus, then this term, I've got the fourth root of 16, and the fourth root of 16 comes out clean. It's a 2. But then I've also got the fourth root of p to the 3rd. And you'll notice that I left that as a radical. I should probably see, well, this first term, if I have like radicals, I can add or subtract those. So p to the 3/4 is like p cubed under a fourth root minus 2. Hey, and that has a p cubed under a fourth root as well. Those are like radicals. If I have one of those radicals and I take away 2 of the same radical, my final answer is negative fourth root of p to the 3rd. All right, so that is simplified, or we could have written it with a rational exponent, called it negative p to the 3/4 power. Those are both equivalent ways of expressing the simplified result of that operation. All right, definitely a lot going on. We've got a long assignment to practice all those different skills, and you can bet that we're going to split this over a couple of days. Take your time, really understand how these properties work together. Once you get the hang of it, just like with most things in math, once you get the hang of it and it becomes practice, it's something that becomes much more efficient. And you can take my word on this. Being able to work with exponents easily will definitely help us out in future chapters and future math classes as well. So here's a look at your assignment. I hope you've enjoyed section 5.2.